The next speaker is going to be Nate Foster from Cornell. Nate's a professor in the computer science department at Cornell, and he's done a really nice body of work bringing programming languages and techniques from that community to bear on how we design and operate software-defined networks, and he's going to describe some of that work next.
Thanks, Jen. So I'm going to talk about how we can design some nice high-level software abstractions for doing consistent updates in software-defined networks. This is joint work with a team split between Cornell and Princeton. So my student, Mark Reitblatt, and at Princeton, Cole Schlesinger is a PhD student, and faculty, Jen and David Walker. So implementing changes to network configurations is one of the fundamental tasks that a network operator has to do. And there are a host of reasons that you need to change configurations, everything from routine maintenance, maybe taking some devices out of the network or putting some new devices into the network, to handling unexpected failures, maybe by routing around a link that's congested or downright failed, to traffic engineering, to things like updating access control lists to implement some refined security policy. And of course, software-defined networking only provides many more reasons to change the configuration of the network, because now we have a program that's actually generating the configurations for the network. And typically, when one makes a configuration change, there are a whole host of invariants that you want the network to have. So for example, you might want the network not to lose packets just because you're making some change to the configuration. You might like it not to break existing connections. You might like it not to create transient forwarding loops. And of course, you don't want it to somehow create new security holes if what you're doing is trying to update the configuration in order to patch a security problem. And unfortunately, managing all these things is quite difficult to do. So I hate to pick on Amazon, but they provided a really crisp example of how hard it is to implement configuration changes reliably just last year. So I'm sure most of you know this story, but in April of last year, Amazon was trying to implement a kind of routine maintenance task, shifting load from one set of routers onto a different set of routers, and they made a mistake. And the upshot of this mistake was that a whole bunch of traffic got sent onto a redundant backup network that wasn't intended to carry that much load. And the resulting congestion triggered a packet storm, et cetera, that basically brought down their whole East Coast data center. So configuration changes are really hard to do right. And in the research community, there's been sort of a cottage industry of proposing little extensions and tweaks to protocols like BGP and IGP to help operators implement configuration changes in a graceful way. So if you scan through the literature, I'll just show you a few papers. You could find many more. You see papers like consensus routing, or reliable BGP, or graceful state migrations, and the list goes on. You also see papers, I like this one. The title is Dynamic Route Computation Considered Harmful. It's by some people who are in this room. And the basic premise of this paper is that network configurations are fairly fraught with peril. And so operators, instead of being so reactive and trying to tweak the configuration of their network very frequently, should take a more measured approach and implement configuration changes pretty rarely. And although this is a somewhat pessimistic view, there's sort of a grain of truth in it. So a couple of years ago, the National Academies did a study of what happened to the internet around 9/11, and they found that while there were some disruptions around Lower Manhattan, for the most part, the internet was actually very stable that day, and in fact, even more stable than an ordinary day. And the reason is operators were staying home. They weren't tinkering with the network. So I find this a little bit pessimistic, and I believe that software-defined networks offer an opportunity to solve this tricky problem and get things right. So my vision is that we can do some work at the level of software abstractions and provide programmers with some tools they can use to implement changes to network configurations in a reliable way. And so instead of having to think hard about how we want to implement graceful network updates for every single protocol, and instead of giving up hope and saying, let's not update the configuration of the network at all, we can actually design some abstractions that address this problem square on. So that's what I'm going to tell you about today. So just as an example to kind of make these ideas crisp, I want to show you a kind of baby application that one might write in an SDN platform like OpenFlow. And this application is intended to be implementing some kind of distributed firewall. So in the diagram you see here, I have 4 switches, 1 ingress switch and 3 filtering switches. And traffic, for simplicity, is just flowing from left to right. So the traffic on the ingress side, I've divided into 2 classes. You have black hat traffic, which is somehow untrusted, and you have white hat traffic, which is trusted. And what I want is that the configuration of this network implements the high-level security policy I've shown on the right. So that diagram may be kind of small to see in the back, but basically what it says is black hat traffic is allowed to flow through if it's to web hosts, but if it's not to web hosts, then it's blocked. And white hat traffic is always allowed to flow through. OK, so there's lots of different configurations we could use to implement this policy. Here's one. I'll call it configuration A. And the idea in configuration A is we're going to use the ingress switch to sort of split the traffic, depending on whether it's black hat or white traffic, and send it to the filtering switches. And in configuration A, all the black hat traffic will go to filtering switch 1. And then filtering 1 will perform the requisite pattern matching and filtering on those black hat packets. And filtering switches 2 and 3 will be sent all the white hat traffic, and they'll just pass those packets through unmodified. OK, so this configuration correctly implements our security policy. And you can imagine that over time, it could be that there's actually a lot of black hat traffic. And so because we're sending it all on this upper path through this network, filtering switch F1 and the links connected to it could start to become swamped. And so we might want to move to a different configuration where we use more of our filtering switches to do the requisite matching and blocking. So we might like to transition to this configuration B, where the ingress switch instead sends all the black hat traffic to F1 and F2, and it sends the white hat traffic to F3, and then changes the filtering rules appropriately to still implement the security policy. So both of these configurations correctly implement our intended policy. But if you start out with a network that's in configuration A and try to migrate to the configuration B, it's rather tricky. And if you just start kind of updating the configurations of individual devices, you can very easily break your policy. So you can cause hosts that should be able to send packets through to not be able to, or you could open up the network and allow black hat traffic to get through when it should be blocked. So the idea behind the work that I'm describing today is instead of having programmers have to deal with low-level details like deciding which order they should install or uninstall individual rules on switches, let's provide them with an abstraction that lets them update the entire configuration of the network in one fell swoop. And this turns out to be quite challenging because even though software-defined networking kind of gives us this illusion of centralized control, we have one controller that's dictating the policy for the network itself is still a distributed system. And you can only update one switch at a time. And so our approach is to design a little construct. You see it here in a teletype font in the middle, which just gives programmers a way to update the entire configuration of the network. And maybe they provide some other information like the topology of the network. And under the hood, we're going to have a compiler and a runtime system that's going to take the description of the whole network configuration, analyze it, compile it down into a sequence of low-level instructions at the level of OpenFlow to contact individual switches and actually install or uninstall rules there. And we're going to design the semantics of this construct to be such that it will actually take us to the new configuration while being reasonable during the transition. And I'll say precisely what reasonable means in a couple of slides. Another advantage of designing such a software abstraction is, although the details of implementing this kind of construct are quite tricky, we can just do the work of actually implementing it once. We can work really hard to make it fast. We can develop optimizations that handle common situations in lightweight ways. And then programmers just don't have to worry about this. They can just use this update abstraction and know that under the hood, the compiler and runtime system are applying optimizations to produce an efficient update plan. OK. So just to show you what this abstraction looks like on our little example, here's a bit of code. You don't have to read the details. It's basically code written in Python for an OpenFlow controller like Nox. And at the top, you see two configurations. They're basically Python dictionaries that describe the complete set of rules that should be installed on all the switches in our example. And the interesting bit is at the bottom, you see the main function that we write for this program. And it doesn't involve any low-level OpenFlow commands. Basically, all we do is we just say, initially, update the configuration of the network to configuration A. And then, OK, wait for the traffic load to shift, maybe by doing some monitoring. And then after a time, update to configuration B. and that's it. The programmer doesn't have to worry at all about which switches to contact, in which order, which rules to install, which rules to uninstall. It's all handled by this software abstraction. OK, so I've showed you what this thing looks like in action. I haven't told you what its semantics is. So very often when I tell people about this work, the first thing that they think they want is, well, I want some kind of atomic semantics. I want this update abstraction to have the property that, OK, I don't know exactly when it happens, but the old configuration is in place for a while, and then there's some point where the network just atomically shifts over the new configuration. And it turns out this is not what you want. For one thing, it would be incredibly costly to implement, so costly that no one would be willing to use it. It would basically require buffering all packets while you're doing the transition. And moreover, it's actually quite difficult for programmers to reason about, because you might have packets that are in flight. And even though the whole network might do some atomic transition, the effect on an individual packet could be that it still sees a mixture of the old configuration and the new configuration as it's being processed through the network. So the semantics that we chose instead for this update abstraction is what we call per-packet consistency. And basically what per-packet consistency is inspired by is, well, I just said that it would be tricky to think about if a packet could be processed by a mixture of the two configurations. So let's just dictate that every packet will be processed by just one configuration. And that's exactly what it says. So every single packet, as it traverses the network, will be processed either by the old configuration in place before the update, or the new configuration that's contained in the update, but not some mixture of the two. And although this doesn't talk about what happens to any pair of packets, when we're thinking about programs in terms of how they process individual packets, this gives us a very robust guarantee. And in particular, for our security example that we just saw, the distributed firewall, you can see that it will be very easy to reason about the correctness of our program, because by the fact that both configurations correctly implement our security policy, having a guarantee which says every single packet will be processed by one or the other, we get the guarantee that our security policy will be invariant across the update. OK, so the other side of the coin, besides semantics, is what is the implementation of this abstraction going to look like? And there's a whole bunch of interesting work to be done here. The first question you might ask is, well, is it always possible to actually implement this abstraction? Or are there somehow impossible scenarios where there are updates that you can't somehow implement? And the answer to that question is no, you can always do this. So there's a general mechanism, which is very similar to two-phase commit, that one can use. The basic idea is to use some bits in the packet to encode a version number. And the version number corresponds to which configuration version is being used to implement, to process this packet. And so to implement an update by the two-phase commit strategy, what we do is we instrument the raw policy given to us by the programmer to add version numbers. And then we install the version configuration in the interior of the network first. And because it's only installed in the interior of the network, it's not enabled. And then after that's completed, we go around the perimeter of the network and install an edge version configuration that causes it to suddenly be used. And then once that's complete, we can go uninstall the old configuration. So this is quite a heavyweight and expensive way to implement an update. But it's fully general and will work with any policy in any topology. Of course, there are lots of other situations where you can get by with a much cheaper mechanism. So I've listed a couple of simple examples. One that we call pure extension is if the update that you're making to the configuration is only adding some new forwarding paths, then of course it's silly to go through and reinstall every single rule at some new version. So you can do something much lighter weight and only install rules that enable those new paths. Dually, if you have what we call a pure retraction, and the new policy is just disabling some paths, then what you can do is disable those paths at the perimeter and then go delete them from the interior. Another example of a kind of optimization you can do is what we call slice updating. So if the update only affects some connected region of the network, then of course you don't have to update all the switches that aren't affected. You can just update the kind of island of switches that are affected. So there's more things you can do. But the point is, by putting this update mechanism into a software layer that sits above the controller, we can do a bunch of analysis of the topologies and policies that the programmer is giving to us and select the best strategy for implementing an update in a way that provides the semantics at least cost. I'd be happy to show a demo. Unfortunately, I don't have time to do it in this short 15-minute talk, but if people are interested afterwards, I have a nice demo showing how you can migrate from one multicast spanning tree to another. And if you did it naively, you could easily create a forwarding loop. But using our update abstraction, you're guaranteed that there are no forwarding loops. So if people are interested, come find me after, and I'd be happy to give you a little demo. One other major advantage of investigating this kind of software abstraction is that it allows us to do reasoning about programs. And because I have a background in programming languages, this is something I'm very interested in. So another thing we've investigated in this work is what are, in a precise and formal way, the semantics of these updates. And we've actually done some work to develop a simple, lightweight, formal model of a software-defined network as a labeled transition function. For those of you who have a CS background, this is sort of like what a finite automaton looks like. And we've proved some theorems. The most interesting theorem that we've proved about this model is any update that's per packet consistent preserves all properties of the two configurations involved in the update. So what this means is, if you want to check that some property is invariant across an update, and you know that you're using a per packet consistent mechanism, all you have to do is check that those properties hold in the two configurations independently. And you don't have to worry at all about all of the intermediate states you might reach during the update, because the per packet consistent update mechanism guarantees that they'll be preserved. Again, you have to grant me a little bit of fun. Since I'm also a PL person interested in formal verification, we've actually done all this in a mechanical proof assistant and proved this theorem formally. So if people are interested, I can show them that as well offline. One corollary of doing all this work on the language side is that we can use this to build a tool for doing formal verification of network programs. So because per packet consistent updates have this property that they preserve all properties, if we want to do formal verification using a tool like a model checker, all we have to do is check that the old and new configurations have the property we want. And we built a little tool that does this. It basically builds a simple, what's called a Kripke structure out of a topology and a network configuration. And then you can feed into this model checking tool formulas that capture common properties like connectivity or loop freedom or black hole freedom or access control or waypointing. And you can check mechanically that these properties hold. So this is quite a nice way to bring some assurance to software-defined networking programs that involve updates. Let me just in the last few minutes say a couple of things about some of the extensions of this work. So I've talked a lot about per packet consistency, which talks about what happens during an update to a single packet. Of course, in lots of applications, you care about more than what happens to a single packet. You care what happens to sets of packets. And there's an extension called per flow consistency that talks about what happens to sets of packets with related headers. And this is useful for building things like load balancers or applications that require some kind of affinity and such. The implementation mechanisms, of course, become much more tricky because the runtime system and the switches need to somehow keep track of which flows are active in the system. And so if you're interested, I can tell people offline about the way that we do that. In terms of ongoing work, we're doing some work on coming up with other kinds of abstractions with weaker but less expensive implementation cost. So things like if you only care about sort of structural invariants like loop freedom, then you may be able to get by with cheaper mechanisms that don't require as heavy-handed as the two-phase commit, for example. And we're also looking at things like abstractions that can handle unplanned change, for example, failures. So if people are interested in hearing more, you can go to our website, freneticlang.org, for papers and some source code, and I'd be happy to take questions.
Questions?
Hi, Leon Putievsky, Google. Very interesting work, thank you. I'm curious if you've evaluated how close the solution is to the optimal in terms of the number of flow modes that you need to perform to switch. So you have this make before break approach.
So I think if I heard the question correctly, it's have we evaluated how close these mechanisms get to the optimal update strategy?
Optimal in terms of how many flow modes, how many changes you need to perform in network to get to that new solution?
No, we haven't, but that's an excellent idea for future work. So I'd love to do that.
Hello, good afternoon. This is Daniel Chung from Acton, Taiwan. It seems to me that you take an initial condition and final condition, and then you use something like an artificial intelligence algorithm or like a car navigator to compute every step and only use steps that are consistent, and to reach like your example of reversing the roles of those filters by breaking up into small steps and do this computation automatically. Is that correct?
Yep.
Okay, so you will need some kind of a complex algorithm to figure out the steps.
Well, I should say, so we have a number of mechanisms. Some are not so fancy, so they're doing kind of straightforward but pervasive instrumentation of policies. And then you can imagine other mechanisms that are doing things like searching through the effective forwarding space of a configuration. And some of our optimized mechanisms do things like that. So that's more of the flavor of what you were describing.
Rob Sherwood, Big Switch Networks. I liked your characterization of packet consistency. I wonder how hard it would be to get to what I'm mentally thinking of as flow consistency, meaning that within a flow, it's either acting in the initial configuration or there's exactly a demarc in time, and now all packets in the same flow are acting on the new configuration. Is that possible? Is that actually what you've actually achieved?
So what we have in our prototype right now uses a fairly crude notion of flow. So a flow is a set of packets separated by no more than k seconds for some fixed k. And the mechanism we use to implement that is basically soft timeouts on the OpenFlow switches. Okay. Now, of course, we'd like to do better. And if you used an architecture like what Jen just talked about, Serval, where end hosts could actually be involved in telling you, hey, this flow is starting, or hey, this flow is terminated, then you could do a much better job. And that seems like the right way to do it long term.
Thanks.
Thanks.